Hey, we're going to talk about work and force. So, first let's talk a little bit about force. Some things you may have heard before. Force is mass times acceleration. F equals ma. You may have heard. Where mass is in kilograms, so mass is how much of something there is. This is very different than weight. We'll talk about that in a moment. Acceleration in meters per second squared. And force is in newtons. Usually the shorthand for that is N, but based off of mass times acceleration, 1 newton is equal to 1 kilogram meter per second squared. So if you have mass, then you need to work toward force, and we include the acceleration due to gravity as 9.8 meters per second squared. So basically, if you're given mass, which would really be in a metric form like kilograms or something like that, and you want force, you'll have to multiply by that acceleration due to gravity, 9.8 meters per second squared. But if you're given a force, then the acceleration would already be calculated in, so you wouldn't have to multiply. Or if you're given weight, which is usually given in pounds versus kilograms, then that is also a force and you don't need to multiply. So it's a little tricky to get used to it, but generally if you see kilograms, that means it's just mass and you need to multiply by the acceleration to get force. If you're given something weight, like in pounds, then that's automatically a force unto itself. All right, so let's see here. Let's talk a little bit about work. Work is force times distance, so the force required to move something so far. Remember, force was in newtons. Distance here is going to be in meters. Work will end up being in a unit called joules. There's also another unit called foot-pound, just kind of depending on the way things are given. 1 joule is a newton meter, which is a kilogram meter squared per second squared. But if we want to talk about the work done over a period to move something from one place to another, we can use an integration. So work is the integral from A to B. That's a starting position to an ending position of the force formula integrated. And we'll see some examples of that in a moment. So hopefully all this comes together a little bit better with examples. So we're going to talk about Hooke's law for springs. So what this is it says the force required to stretch or compress a spring. So either push a spring together or try and pull it apart from wherever it is at ease, at rest, is proportional to its position. So we get a force constant here where the force is equal to some multiplier times the position, the movement. Okay, F equals kx. So basically that's the force to move at x units. Okay, and there's some multiplier there that is constant. So let's see that in action. Okay, so this is an example from the book. It says a spring has a natural length of 10 inches. Okay, so that's its resting position, 10 inches long. A 800-pound force stretches the spring to 14 inches. Okay, and it says find the force constant. So what we're looking at here is we're looking at force equals kx, where the force would be some constant over the distance changed. So they tell us the force is 800 pounds, so that's already a force. We're looking for the constant, so 800 equals k, and it went from 10 inches to 14 inches. So how far did it move? Well, we used that 800-pound force to move it 4 inches. So if we divide that out, the k here would be 200, and what would that be? That would be pound inches, so that's not really pound feet or foot pounds, but the constant here is 200. And then it says how much work is done in stretching the spring from 10 to 12 inches. Okay, so now that we know the constant, we can set this up as force equals that multiplier 200 times the distance change, which would be 200. Okay, so in that case the force would be 400. Okay, and then it says how far will the spring be stretched by a 1,600 pound force? Well, we're going to set that up again. So we've got our force, which is 1,600 pounds, times our constant 200 times x, and if we divide that out, x would be 8 inches. So it's stretched 8 inches, so stretched 8 inches. And just to make sure it doesn't get confusing, we could say to a length of, it was 18 inches. Alright, so let's take a break there to absorb, and we will, wait a minute, any more examples here? Yeah, let's just keep going here. It says we have a force of 90 newtons to stretch a spring 1 meter. How much work will it take to stretch the spring 5 meters? Okay, so we know it takes 90 newtons to stretch the spring 1 meter. So if we were to set that up, we could say that the force equals kx. So the force was 90, and that would be k times, in this case, 1. So the k is 90. So when we use that, we can come over here and we can kind of make our own little force function. Our force function will be 90x. So that's a function to figure out basically how far we stretch it, how much force will be used. So we're asked here for work. So our work would be an integral from, in this case, we're going to stretch it to 5 meters. Okay, and we're, hold on one second. Okay, so we're going to stretch it 5 meters. So we start off with it at rest. We just used the 1 up there to figure out the force function. So it's going to go from at rest, and we're going to stretch it 5 meters. So from 0 to 5, and the force function is 90x. So we're going to integrate this to get the total force done. Okay, so in this case, the work will be, this will be 45x squared. We're just integrating, so that the x goes up to x squared, divide by the 2, and we're going to evaluate that from 0 to 5. So then I'm going to let x equal 5. So that'd be 45 times 25, and then we'll let x equal 0, which will be 0. So 45 times 25 is 1100. I lost my cursor somewhere. Where'd you go? Oh, it's up here. Sorry. I don't see it though. Sorry, I feel so weird here. Oh, that's it. 1125 joules. So this was in, the work was in newtons, and the length was in meters, so Newton meter is the joule. So the work done to stretch this thing, and I don't know why my cursor, I can't see it, is 1125 joules. Alright, so let's try a different one. There, okay, I see it. Okay, so this is another one. It says a scale is compressed 1/16 of an inch by a 150-pound person, basically. Okay, so the 150 pounds, that's a force. So it says how much weight should be applied to compress the scale 1/8 of an inch. Well, let's see here. We first of all need to backtrack and use our force equals kx. So we know from the given information that we have a 150-pound force to move at 1/16 of an inch. So the k here will be 16 times 150, which would be 2400. So that's the force constant. So when I want the force, I'm going to say the K, which is 2400, times the 1/8 of an inch. So that force will be 2400 times 1/8. So it looks like that is a 300-pound force to make it move 1/8 of an inch, and that is proportional, like we said. Sorry. Alright, so then it says how much work is done compressing the scale 1/8 of an inch. So we're going to take this thing from rest to 1/8, and the force function will be our K, which is 2400x. So that's our force function. Okay. Dx. So we will integrate that thing, so it will be 1200x squared from 0 to 1/8. So let's see here. 1/8 squared. So I'm going to get, when I multiply that by 1200, 18.75. Okay, and so what we were working with here, let's see here, we had pounds up here, and we've got inches, so let's see what we can do with that. So we can call that pound inches if we like, instead of foot pounds. So let's see here, pounds inches. If we want to change that to foot pounds, we know there is a 12 inches in a foot, so I mean we could divide that by 12 if we wanted to, and basically we could say this is a 1.5625 foot pound. Alright, I think we'll stop there because we got something different going on next.